Okay, the next Bessey shuffle we will look at is the one over here on the far top left. The J stands for judicious, and the RC simply reminds us that the stay stack principle is in force, and more specifically, the cards are going to be dealt out into a number of piles for which the number of piles is a divisor of the packet size. Now, the divisors of 8 are 2 and 4, setting aside 1 and 8. So here, for this judicious RC, we will deal into 4 piles, and we will stack the piles in a way that we have not yet demonstrated within our discussion of Bessey shuffle diagrams. Okay, so how this works then is we're going to deal out the cards into 4 piles. Once we've done that, we're going to stack the first pile on top of the third, the second pile on top of the fourth, and then, given those 2 piles, we will stack the left pile on top of the right. Now, the claim is that such a shuffle leads to the following permutation expressed in cycle notation. So why don't we go ahead and just kind of verify this. So if you remember, we began with Cauchy's 2-line notation for our permutation. So the top row will just be 1 through 8. So what we do is we work with an ordered packet, and I've just numbered these 1 through 8. We perform our shuffle, and then we look at what results. Okay? So the shuffle here is simply dealing into 4 piles, just like this, where it's understood that this is pile 1, 2, 3, 4. Okay, so according to our stacking here, we stack 1 on top of 3 and 2 on top of 4. And finally, we stack the left on top of the right. Okay, now if you've watched some of the other videos on Bessey Sequences, we've referred to this as the leapfrog shuffle, where you're leaping over the neighbor of each pile, moving from left to right in this case. Okay, so what does that result in? What do we finish with here? Looks like it's a 5, 1, 7, 3, 6, 2, 8, 4. That's what we get. 5, 1, 7, 3, 6, 2, 8, 4. Okay, so that is the new ordering after that shuffle has been applied. Okay, now given that information, we can now rewrite that 2-line notation into 1-line notation, also called cycle notation. Okay, so how this works is you begin with 1 up here, 1 goes to 5, so I have an arrow from 1 to 5, 5 goes to 6, 5 goes to 6, 6 goes to 2, so I have an arrow from 6 to 2, 2 goes to 1, so it wraps back around. So that gives us a 4 cycle. So we can compress all of this information, what's happening with those 4 values, to just this set of symbols here. Okay? Now for the remaining values, we get the following. If we begin at 3, 3 goes to 7, so we have an arrow there. Where does 7 go? 7 goes to 8, 8 goes to 4, and then 4 goes to 3, which wraps around, so that closes that cycle. So we can compress all of that information into this set of symbols right here. So 3, 7, 8, 4. Now color-coded, we obtain the following. So if we just rewrite the terms in the cycle notation of our permutation, we'll obtain the following. Remember from earlier, 1, 4, 6, 7 are color-coded black. 2, 3, 5, 8 are color-coded red. So if we go through and perform our color coding, we'll see that black 1 goes to red 5, which goes to black 6, which goes to red 2, which wraps around and goes to black 1. Red 3 goes to black 7, which goes to red 8, which goes to black 4, which wraps around to red 3. So what's happening here is each black value is being assigned to a red value and vice versa. So each value gets sent to a value of the opposite color. In other words, inversion has occurred. And we can see that in the diagram on the left. So in our very first video, we showed you how to draw these. So 1 goes to 5, so we have an arrow from 1 down to 5. 5 goes to 6, so we go up to 6. 6 goes way over here to 2, so there's an arrow from 6 to 2. 2 goes up to 1, straight up like that. And that completes that cycle, actually. And we also call that an orbit. The set of values 1, 2, 5, 6 form an orbit, meaning they get assigned to values within that set. And then the remaining portion of the diagram, if we begin at 3 right here, 3 goes to 7. So 7's up here. 7 goes to 8 there. 8 goes all the way down here to 4. And then 4 goes to 3. So it just goes right there and completes that cycle. Now I have a note here at the bottom that this particular shuffle is the inverse of 42. So that is a shuffle that we'll be looking at later in this little series on Bessey shuffle diagrams. So I'll remind you of that when we get to shuffle 42. And then up here I have a summary of the fact that inversion occurs. 1, 4, 6, 7 get assigned to 2, 3, 5, 8 in some order, and 2, 3, 5, 8 get assigned to 1, 4, 6, 7. So inversion, in fact, does occur. Now what that means, if you remember, when it comes to Bessey sequences, so why don't we just tie that in quickly again from last time. So here is the kind of quintessential Bessey sequence if you want to begin with a 1. So 1, 0, 0, 1, 0, 1, 1, 0. The claim is that this shuffle will invert this. Well, inverting this simply means that we'll replace zeros for ones and ones for zeros. And in particular, it just means that we're going to get the second Bessey sequence of order 8, which is 0, 1, 1, 0, 1, 0, 0, 1. So let's go ahead and just show you that inversion, in fact, occurs. So once again, what was this shuffle? We deal into 4 piles, like so, from left to right. And then we're doing this kind of leapfrog. We're going to go take this one, this is pile 1, hops over and gets stacked on top of pile 3. 2 hops over and gets stacked on top of pile 4. And then in this particular shuffle, we're going to stack left on right. Okay? So the claim is we should now get 0, 1, 1, 0, 1, 0, 0, 1. Okay? So that is what we get. Inversion, in fact, occurred. So you may want to think about the practical value of knowing inversion occurred. So for example, if all of the 1s were the aces, the 4 aces, and the 0s were the queens, then if we had started with the 1s on top, like we did, okay, so if we started with an ace on top, that would mean we'd have a queen on the bottom. So this is where so once again, this is where we started before the shuffle, right? This is where we started. And so because inversion occurred, what that will mean now is instead of an ace being on top, after we perform this shuffle, we are guaranteed to have a queen on top with an ace on the bottom, okay? And so at the end of this video today, we'll show you a simple application of all of this that involves just ordinary cards. Okay,